Good morning. Okay, we'll get started here. Physics 4a. So we're going to sort of take what we did last time and take it one step farther. Here's the situation we had last time. We had a come on. There we go. We were given this set of velocity versus time graphs, these 6 velocity versus time graphs, and we use those to figure out the acceleration versus time. I've copied over what we did last time here. I filled it in. So we did that last time. Hopefully you reviewed that. You've got that. So today what we're going to do is we're going to take those velocity versus time graphs and fill out the corresponding position versus time graphs. So using these velocity versus time graphs, let's do the position versus time graphs. And let's, how about we start with, which one should we start with? Let's start with D. Let's do D, and we'll kind of go through them one at a time. That way, if you don't get it at first, you'll hopefully be with it by the end. So let's start with D. You're going to take that velocity versus time graph. The velocity is 2. I put some numbers in there, 2 meters per second, and it's constant for 10 seconds. And we're given, what are we given? We're given the fact that at t equals 0, the particle was at x equals 0. It starts at the origin at t equals 0. Yeah, we did the last time we did the acceleration graphs, and I've copied that over here. So we're not going to do that again today, but you can practice it later if you haven't already. This time we're taking that velocity versus time graph and coming up with the position versus time graphs, and we're going to start with just D. Okay, so let's talk about this one, and then I'll give you some time to do some of the others. What we're looking at, of course, is the area under the curve. Remember, when we go down, when we go from position to velocity, we look at the slope. And when we go up, right, we look at the area, we integrate. Take a derivative going from position to velocity. So the area under the curve, let's take a look here. We've got the area is equal to 20. 20 meters, right? And so that's going to equal the change in x. That's a delta. So if x started at 0 at t equals 0, and at t equals 10, it's at 20, then we've got our endpoints. Now we just have to figure out what happened in between. And we know that the slope of our x versus t curve, the slope of position versus time, is the velocity at that instant. So the slope here has to correspond to the velocity at that point. The slope here has to correspond to the velocity at that point, right? The slope here has to correspond to the velocity at that point. Well, the velocity is the same everywhere. So that means the slope has to be the same everywhere in our position versus time curve. And if the slope is the same everywhere, it's a straight line. So I get my straight line tool and I connect those points with the straight line. So that's our position versus time, given that velocity versus time. Now, if we were not given this initial condition here, if we weren't told where it was at x equals 0, where it was at t equals 0, then we could all have different answers. Because when you do this, the only thing this tells you, the area under the velocity versus time curve, tells you the change in position. It doesn't tell you any absolute number. You have to know either something along the way, where you started, where you ended, something, right? It only tells you the change. So one of us might have had this graph here. Somebody else might have had this graph here starting at -20 and ending up at 0. That would also work, right? Somebody else may have said theirs started at 20 and went up to 40, right? That would have worked too. As long as we all had the same slope, those would all be correct. But since we were told that t equals 0, it was at the origin. Now there's only one correct answer, and this is it. Okay, let's move on. Let's do A. So A also has constant velocity, but it's -2 instead of +2. So we're going to follow the same process, the same thought process for this one. We'll find the area under the curve, and that'll tell us the change in position. We know we're starting at x equals 0 at t equals 0. So where is x? What's our position when t is 10 seconds? So we come down here and we say the area under this curve is equal to -20 meters, because it's below the x-axis, right? It's -2 times 10, -20 meters. And so that has to equal delta x. That's an x. Why isn't it writing it? Come on. There we go. And so and then we ask ourselves, okay, we know where it started, we know where it ended, what happened in between? And the slope has to be the same everywhere because the velocity is constant. So if the slope is the same everywhere, it is a straight line. We just connect those 2 points with the straight line. All right, let's do, how about B? Let's do B. Yeah, so here we have a velocity that's changing, right? That means the slope of your position versus time curve is going to be changing, which means not a straight line. So same process, right? We'll start with the area under the curve here. So 1/2 base times height, that's 10. The area is 10 meters. So that has to equal delta x. So if we started out at 0, then it ends up at 10. I'm changing my scale here a little bit, but that's okay. Now the question is, what's the shape like? So if we look at this point here at t equals 0, the slope of the position versus time curve has to be a big positive number. So the slope has to be a big positive number here. Then it goes down, right? Then it's a smaller positive number. And out here, the slope of the position versus time curve at t equals 10 seconds has to be 0, right? At t equals 10 seconds, we have to have a slope of 0. So we start out with a big slope, and it ends up being a slope of 0. So it's concave down. Concave down. And how else do we know that it has to be concave down? Well, we look at our acceleration versus time, right? The acceleration is negative. Oh, my OneNote crashed. There we go. The acceleration is negative, and the acceleration is the second derivative of x versus t. So the second derivative negative means concave down. All right, how about we do one more? E, let's do E. And you can do C and F later if you'd like. Okay, so we're doing E now. Oh, sorry. Screen sharing has stopped because it, let me fix that. Crashed. There we go. Okay. So for the first half of this, for the first 5 seconds, the area under the velocity versus time curve is negative. For the second 5 seconds, it's positive. So it moved in the negative direction the first half of this time period. It moved in the positive direction the other half. And we add those two areas together, we get 0. So the change in position has to be 0 over the whole 10-second time period. So we know it started at 0. We know at 10 seconds, it's 0. And we know at 5 seconds, it's at -5. Where's 5 seconds? Right about there. So now we have to connect these dots, right? Well, let's look at the slope. The slope of the position versus time curve at t equals 0 has to be -2, a big negative number. Then it gets smaller and smaller and smaller, and the slope is 0 at t equals 5 seconds. And then we have a big positive, a slope of +2 at t equals 10 seconds. So the slope, I'll use green, the slope is a big negative number here. It's 0 there, and it's a big positive number there. So when I go to fill this in, I get something that looks like this. Kind of, sort of. Concave up, it's a parabola, part of a parabola. Okay, I'll leave the other two for you to do on your own. Okay, so we're gonna tackle this problem. We've got a car or a truck, I guess it is, moving, and it's slowing down. So we're given some information. Over a 40-meter period, the whole thing takes 8.5 seconds, and it smoothly slows down. That means constant acceleration. You have to learn some of the secret words there in physics problems. Smoothly slowing down means constant acceleration. And it ends up with a final speed of 2.8 meters per second. So we want to find the original speed and the acceleration. So I want to do this two ways. I want to use our equations and sort of do it that way. And then I want to take the graphical approach. We'll just do it graphically. We'll make a graph of velocity versus time and see if we can figure everything out from that. So what should we do first? How about we do it graphically first? So let's make a graph of velocity versus time. And I'll give you a minute to do that. See if you can graph velocity versus time. So we know it starts out at some initial velocity. We don't know what it is. Starts out at some initial velocity, and it slows down. 8.5 seconds later, it's going some slower speed. And we know what that is. That's 2.8 meters per second, right? It's displacement. Area under velocity versus time is displacement. And we're given that it's constant acceleration. So what's the graph look like between these 2 points? How do we connect these 2 points? A straight line or a curve? A straight line, that's right. Because the slope, the derivative of velocity versus time is acceleration. We have to, if the acceleration is constant, the slope of this line has to be the same everywhere. So it has to be a straight line. So there's our graph. I'm just going to separate this so I can find the area easier. So we've got velocity versus time, and we know that it spanned 40 meters, a distance of 40 meters. So the area under this curve has to equal 40 meters. So let's figure out what the area is. So we have a triangle there. I'll break it up. I've got the top part here is 1/2 times the height of that triangle is v initial minus 2.8 times the base, which is 8.5. And then I'm going to add to that the area of the part underneath. And that's just a rectangle, 8.5 times 2.8. And I say this has to equal 40 meters. So my initial velocity is, I got 6.61. Is that what you got? Okay. Confirmation from one person. Now, how are we going to figure out our acceleration? They asked for two things, right? They asked for the original speed, so we've got that. Started at 6.61 meters per second, ended up at 2.8, 8.5 seconds later, and it covered a distance of 40 meters during that time period. So now we want to know part B, what's the acceleration? Well, the acceleration is just the slope of that line, right? So the slope is the change in velocity over the change in time. And we've got V final minus V initial over delta t. Okay. Good. Okay, so I think, maybe you're seeing that this graphical approach is kind of nice. Yeah, in this problem is not that complicated. Let's do it using the equations. I think you'll see it's kind of about the same either way. But later on, we'll do a problem where you'll see the graphical approach is really the right way to do it. And that's anytime you have a complicated situation like a race where two objects are racing and one passes the other one, doing those with the equations can become a nightmare. You have all kinds of equations and you have to solve simultaneous equations. But the graph, you can pick points out on the graph and see that it's much easier to solve that way. So we'll do that later on. All you need to do is find the area under this shape, right? You're finding that area. However you'd like to do it is fine. I decided to break it up into a triangle and a rectangle. Okay, now let's take the second approach. We'll use our kinematics equations. And we can use these because we have constant acceleration. So we have our truck moving. It's got some V initial, and at some point later has V final, and it's slowing down. And we can pick, we'll just take that as our positive direction. So that way everything's positive. So I like to make a little chart like this when I do these kinematics problems. This is just one-dimensional motion, right? We've got an object moving in a straight line. So the first thing we really care about, there are 5 things that help us to define the motion of this object. The first one is the change in position. I usually write it as x initial and x final, but really what we care about is the change in position. And then we have the initial velocity, the final velocity, the acceleration, and the time. So I make a little table like this, and that just helps me organize what I know, what I'm missing, which equation I'm going to use. I can spot it from using this chart. So let me fill in what I know. The first thing you have to do is define your origin and your positive direction. So let's have it starting at x equals 0, and the positive direction will be to the right. So that means this is x equals 40 over here, right? So it started out at x equals 0. at our final position is 40 meters. We do not know our starting velocity, but we know it ended up at 2.8 meters per second. We don't know our acceleration, but we know this whole thing took 8.5 seconds. So the key with this chart, as long as there's not a bunch of zeros in there, if you have a bunch of zeros, then that doesn't help. But as long as you have information there and everything, you can fill in. As long as you have 3 of these boxes filled in, you can solve for the other 2. So we have 3 of them. We have delta x, we have v final, and we have time. So we can solve for v initial, and we can solve for the acceleration. So I would pick, if I'm solving for v initial, and I don't have acceleration, I would pick an equation that's missing acceleration. So you look at your kinematics equations. I had them on the board here yesterday. You look at your kinematics equations and you say, which one is missing acceleration so I can find v initial? Well, this one is x final equals x initial plus the average velocity times time. So I know everything here except for v initial. So I can solve for v initial right now. So I just plug in what I know and be very careful to plug in the correct sign. In our case, everything is positive, but that's not usually the case. So be careful to, if you had a velocity of negative 2.8, make sure you plug in negative 2.8 here for the velocity. But our numbers are all positive. So x final is 40, x initial is 0, v initial plus v final over 2 gives us the average velocity, and the time 8.5 seconds. And so we get v initial is, well, what does it have to be? Same as what we got in the previous method. 6.61 meters per second. And then we can use any equation. We can, to solve for acceleration, the easiest one to get acceleration from is v final is v initial plus at. And now that we know what v initial is, we can use this equation. And that gives us 2.8, 6.61 plus a times 8.5. A is negative 0.448. Is that right? That's a 4. Okay. So I think it's kind of a fun technique to try both when you're working problems, see which one you like better. The graphical approach is kind of nice. And like I said, there's a few problems where it's really the right way to solve it. And we'll do one of those later on, where we have a race, 2 things, one passing the other one. You'll see how nice it is then. But most of the time, I probably, for simple kinematics problems, I probably just jump right into the kinematics equations. Make that chart for yourself, get in the habit of making that chart, and that just helps organize your thoughts, your data. What do you know? What are you trying to solve for? What's missing? That kind of thing. Okay, let's do this one. Let's do, if you're given this acceleration versus time graph over here on the right. We want to know which of the graphs below would be the correct velocity versus time graph. Given that given the acceleration versus time graph, which velocity versus time graph corresponds to that? Okay, I'm going to cut it off. Almost everyone has the right answer. A few people have something else, but almost everyone got D. D. So what are we looking at? Remember, when we're going from velocity to acceleration, I always like to picture these graphs, position versus time at the top, velocity versus time right underneath that, and acceleration versus time right underneath that. And when I go down, I'm taking derivatives, right? I'm looking at the slope. When I go up, I look at the area under the curve equals the change in the one above it. So velocity versus time, what the slope of the velocity versus time curve gives us the acceleration. So the acceleration never changes here, it's constant. That means the slope has to be constant, has to be a straight line, right? So that rules out E, and it rules out C because C would give us a 0 acceleration, right, in there, right? So that those two are ruled out. Then we see that it has to be a positive. The slope has to be positive here and negative here. The slope has to be positive on one side, negative on the other half. And so D is the only one that has a positive slope and then a negative slope. All right, let's do, we're gonna, from the same graphs, same acceleration versus time, same graphs here, but instead of being velocity, we want to know these are all going to be position versus time, x versus t. Pick the one that gives us the right position versus time curve. Oh, sorry. You're waiting for the poll. There you go. Okay, I'm going to cut it off. Almost everyone has the answer of E. Few people, other ones, but almost everyone is E. So that is correct, E. And one thing you want to look at, right, if you're taking two derivatives of something, if x versus t is a straight line, right, so all of these are straight lines except for E. All of them are straight lines. So if we're taking two derivatives of a linear function, we have to get 0, right? So it can't be a straight line. There has to be a curvature to it. So the only one that has a curvature to it is E. And let's see if E makes sense. So for the first half, the second derivative is positive, which means it's concave up. And for the second half, oh, sorry, I'm looking at the wrong one. First half, it's the second derivative is positive, and for the second half, the second derivative is negative. So it's concave up for the first half, and it's concave down for the second half. So that makes sense. Or since we knew that D was the correct velocity, we could have gone from D, tried to figure it out from D also. Oh, sorry, did my my sound, looks like my sound went out for a minute there. Sorry about that. I'm told that that's a problem, a known problem with the Surface, which is what I'm using, but I'm not sure. I do have a better microphone coming, but I was told by somebody that it's not going to matter. Okay. All right, we're awake now. Sorry about that. Let's do one more. Now we're going to take this position versus time graph and figure out the acceleration versus time. And I will launch a poll here for you. What am I doing? Given that position versus time graph, find the corresponding acceleration versus time. If it helps, do the intermediate one. See if you can find the right velocity versus time graph. And then from there, find the acceleration versus time. Is there one on here that would be the velocity versus time? Remember, we're trying to find acceleration versus time. If it helps, do the intermediate step. We're given position, S is position. We're given position versus time. We want to find acceleration versus time. If you have to do the intermediate one, draw the velocity versus time in between. You can do that. Can you change your mind in a poll after you've submitted it? Let me relaunch it. Let's redo this poll. Okay, we're going to redo this poll now that you've had a chance to think about it. Some of you are falling into the same trap you fell into the first time. Okay, we're about 2/3 of the people voted. Okay, I'm going to cut it off now. We've got 75% of you voted. Okay, so the majority did get it correct. But a lot of you fell into the trap and did the found the graph of velocity versus time, not acceleration versus time. So if you look at this, if you look at this position versus time curve and you draw the velocity versus time, you're going to get a positive slope. The slope is positive and constant, and then the slope is negative and constant. So you get a graph that looks like that, right? So this would not be acceleration. This would be velocity versus time. Then you take the derivative of this, and the derivative of this gives you 0. here, it gives you 0 here, and there's a discontinuity in the middle, right? It gives you some kind of a spike. So B is the one that has the correct acceleration versus time graph. You okay with that? Okay. Now, any questions on that? We okay? All right, so what we want to do, we want to get into talking about free fall now. So free fall means that we only have gravity acting on our object. So if we ignore air resistance, where that's what we'll just have, gravity will be the only force acting on our object. You throw something up into the air, right? Something flies off the table towards the floor, something like that. That's free fall. And since right now we're still only talking about one-dimensional motion, not 2 dimensions, right? Just 1 dimension right now. Then we will limit ourselves to things moving straight up and straight down, right? Dropping something or throwing something straight up, something like that. So linear, straight, one-dimensional motion, and free fall meaning that it's only the force of gravity acting on it. So why don't we do this? Why don't we take a 10-minute break, and then we'll do our free fall problem. Okay. So about 10:58. We'll come back a couple of minutes before 11 o'clock. Let's take a 10-minute break now and stretch your legs, move around, get the blood flowing, and then we'll pick it up again in 10 minutes. I'll pause the recording. So we want to do free fall. We've got this situation. So in free fall, as I said, the only force acting on our object is gravity. And that means we know what the acceleration is, because the acceleration of gravity lowercase g, 9.8 meters per second squared. So let's look at this problem. You're standing at the edge of a cliff. That's you. And you've got a ball here, and you throw it straight down. Let's just call that V naught. So you throw it straight down. We've got some height here. You're above the cliff. And if we're given the initial and h, we want to find the final velocity. We could also find the time. Yeah, sure. Okay. So I'm just going to outline what I think are the right steps to get you to the right answer. These problems really aren't very difficult as long as you take the time to get the details correct. So the first thing you need to do when you do a problem like this is define the origin and the positive direction. Okay, so let's do that. It can be anywhere. Okay, the 2 places that kind of make the most sense are the starting point or the ending point, but it could be anywhere. If you want your origin to be right here in the halfway up the cliff, That's fine. Most of us would probably pick the lowest point in the problem maybe for our origin. So that's what I'm going to do here. I'm going to say that this is my y equals 0. And you can pick any direction you want to be positive. Up, down, doesn't matter. I'm going to pick up to be positive since that's probably what you would do. But actually what you'll see here in a minute is that for a problem like this, if you picked the starting point to be the origin and down to be positive, everything becomes positive. All of our numbers are going to be negative. We'll talk about that when we get there. But negative numbers aren't that hard to deal with. So let's just keep going. This is probably what you would have done, right? Now I fill in my chart. So we've got, I'm going to call this y motion since it's vertical. We've got y initial and y final, right? That's really delta y. We've got v initial, v final, acceleration, and time. So let's fill in what we know. We know if we define the base, that's why you have to define your origin and your positive direction first thing, because you can't fill in this table otherwise. So now I know where my origin is. So where am I starting at? Well, why don't I just give you a minute to fill in this table based on my origin and my positive direction. So y initial, where is our ball at the beginning of this problem? It's at h, right? At distance h above the ground. I'm just going to, just to make it really clear, I'm going to put positive h, but I don't really need the plus sign there. Where is it at the end of the problem? It's almost at y equals 0, right? It's at 0 because obviously the ball is going to hit the ground and come to rest, right? But when I say v final, find v final, what I mean is the velocity of the ball the split second before it hits the ground, okay? Maybe I'll write that here. Just before hitting the ground. We can't solve this problem in one step till where it comes to rest on the ground because we have two different accelerations. Remember, our kinematics equations only work for constant acceleration. So while you're throwing it, while the ball is in your hand, it has some acceleration that's taking place. As soon as you let go of it, the acceleration changes and it's only gravity acting on it. So this problem that we're looking at here takes place from the split second after the ball leaves your hand to the split second before it makes contact with the ground. That's what we're talking about here. So the ball has just left your hand, only gravity is acting on it, and it just is about to hit the ground, because as soon as it makes contact with the ground, there's a big upward acceleration from the ground interacting with it, causing it to stop. So that's a different problem. We'd have to break this up into different problems if we were trying to, if we were given the acceleration of the ball while it was interacting with the ground, we could probably find how long it takes to come to rest, something like that. But for this problem, all we're concerned about is free fall. Gravity is the only force acting on it. So the split second after it leaves your hand to the split second before it makes contact with the ground. And our initial velocity was given, it's v0 in the downward direction, which is our negative direction. V final, we don't know. We're trying to solve for that, right? Acceleration, we do know. It's just the acceleration of gravity, which is 9.8 meters per second squared, but it's in the downward direction, which is our negative direction. And then time, we do not know. Those are the two unknowns that we can solve for. So we pick an equation. So if I'm trying to solve for time, I would pick an equation that's missing v final. And this equation is missing v final. So I would use that. I would plug in my numbers. I'd solve for time. Now there's another equation. So let's do that. So I would do that. I would get y final is 0. Y initial is 50. Oh, sorry, I didn't give you numbers here. Let's let v0 be 30 and h be 50 meters. How about that? I know you all like numbers, right? So this is going to be 50. This is going to be minus 30. Okay, so if we put some numbers in here instead of just doing it symbolically, we'll get y final is 0, y initial is 50, v initial is negative 30. Just be careful to keep your negative signs, carry them through your equations. You have a t here, 1/2 acceleration is minus 9.8, and a t squared. So we have a quadratic, right? And we get our time is going to be either negative 7.49 seconds or positive 1.36 seconds. And of course, negative time doesn't really mean anything to us, so we'll take the positive root. So it takes 1.36 seconds to hit the ground. Now we want to find v final, right? So one thing you could do is to pick, if you're not sure you got the right answer for time, see if you can find an equation that's missing time and then solve for v final. If you're pretty confident in your answer you got for time, then any other equation, pick the simplest equation you can find and get v final. But I'm gonna go ahead and point something out here. I'm gonna use this equation. V final squared is v initial squared plus 2a delta y. So this equation is missing time. So I could use it right off the bat to get v final. But this equation, you have to be careful when you use this equation. Let's see why. So let's plug in our numbers and let's solve for v final. V initial was 30, right? Minus 30 squared plus 2 minus 9.8. and delta y is y final minus y initial. This is going to be 0 minus 50, right? And so we end up with v final is equal to, so we're going to be taking the square root, right? So whenever you take the square root, there, I didn't write down what that was. It's 43.4, right? It's going to be the square root. V final squared is the square root of 1,884. So V final, what is V final? Is it 43.4 meters per second? No, because whenever you take a square root, the root, you could be positive or negative, right? So V final is plus or minus this, right? Just like with time, we got two roots here, and we said, oh, the negative one doesn't make sense. Let's throw that away. We'll pick the positive root. Time can't be negative. Well, down here, we're going to get two roots for V final. And we're going to say, well, which one makes sense? Is the final velocity up the split second before it hits the ground? Or is it down the split second before it hits the ground? It's down, and down is our negative direction. So we would pick the negative root here. I just wanted to make that point. This equation here has that inherent flaw in that it doesn't tell you the sign of V final because you have to take a square root at the end. It only tells you the magnitude. Okay, so anyway, we would pick the negative. Okay, something like that, close enough. I may have rounded off a little bit here. Okay. So why do we get these two times? I wanted to mention why these two times. So what these kinematics equations are doing, they're just filling in the mathematics, right? It doesn't know negative time isn't realistic. It just knows that there's a mathematical equation here, and it's filling in the math. So let's think about what we got here. If we plot our y versus time, we started out here, and we threw the ball down, and it ended up hitting something like that. Maybe I'll move it over a little bit. Yeah, it's hard for me to draw it. It's going the wrong way for me. I'm right-handed. How's that? So at 1.36 seconds, it's hitting the ground, right? That would look something like that. And our velocity versus time, right? It starts off with some negative velocity, and it goes at 1.36 seconds. It's going to be down here somewhere. Something like that, right? And what's our acceleration versus time look like? It looks like a straight line, constant, negative 9.8, right? Okay, so far so good. So what's the equation? Why does it come up with this negative 7.49 seconds? because it's filling in the curve here. It says, well, I know this curve has to look like a parabola. When I plot y versus t, it has to look like a parabola. So I'm going to just fill this in. And where does it hit 0 back here? At negative 7.49 seconds. If I was standing on the ground and I threw the ball up at 7.49 seconds earlier, at t equals 0, it would be coming down at the top of the cliff, right? It would go up higher than the top of the cliff here, right? That's more than h. And then it would come down, it would be at h at t equals 0, 7.49 seconds later, and 1.36 seconds after that, it would hit the ground. So that's why we get a negative root there. It's just filling in the parabola. It doesn't realize that you couldn't have gotten something before t equals 0. So we just ignore that. Okay? So now what I want to do is we'll do the same problem, not this one. That's for later. We'll do the same problem. You standing on the cliff, but instead of throwing the ball down, you're going to throw the ball up, straight up into the air this time. So here's our cliff. Here is you. There's the ball. It's going straight up. It's going to go up, turn around, and hit the ground, right? So given the initial is 30, I'll just use. And same cliff, right? So h is 50. We're going to find v final being the split second before it hits the ground, and the time it takes to do that. Okay, so what are our steps here? Step number 1, what's the first thing we're going to do before we do anything else? Yes. Define the origin and positive direction. Absolutely. So just for the sake of simplicity, why don't we pick the same ones? Most students like the lowest point in the problem to be y equals 0 and up to be positive. But, oh, I was going to point out, let's go back to that previous one. So I picked the lowest point to be 0 and up to be positive. But we were standing on a cliff throwing something down. So what ended up happening? Everything ended up being negative. Delta y was negative, right? Delta y is this number here. That was negative. Our acceleration is negative. Our initial velocity is negative, right? Negative, negative. The delta y is final minus initial, right? Negative. Everything was negative. Is that a problem? Not really. We know how to add and subtract, multiply negative numbers. It's not a big deal. But if we had picked our starting point as y equals 0 and down as positive, all of these would have been positive. Is that easier? I don't know. I say just stick with something you like. You like the lowest point to be 0 and up to be positive, stick with that. That's fine, whatever. But it doesn't matter. You can pick any direction you want to be positive. Just define it and be consistent. Okay, so we've done that. Now we can fill in our chart. Those are the 5 things that we need to sort of define the motion of this object. Go ahead and fill that in. Actually, go ahead and solve for the 2 things we're looking for. So one thing that's tempting, a lot of students like to break this problem up into multiple problems. I know these problems are fun. And if you can break it up into 2, if you can make it into 2 problems, that's twice as much fun as solving 1 problem, right? But you don't have to do that. You don't have to break this up into going to the highest point first and then going to the ground next. You can go right from the beginning to the end because the acceleration never changes. The force of gravity never changes on this object. As the ball is going up, gravity is pulling down on it. When it gets to the top, gravity is pulling down on it. On its way down, gravity is pulling down on it. The acceleration is the same everywhere. So we can go right from the beginning to the end, just make it 1 problem. Okay, so we went through, we found our final velocity, and and then we can find time. And I'll use y final, y initial plus v initial t plus 1/2 a t squared, 0, 50 plus 30t, to 9. And I get t is either minus 1.36 or plus 7.49. And of course, we need the positive root. Okay. So, were you surprised by this result? We get the exact same velocity that we got when we threw the ball down. Throw it down, throw it up, it didn't matter. Why is that? So let's talk about that for a second, because that's worth thinking about. Okay, so this is what we did. Let's make a little motion diagram. We've got a ball here, t equals 0. And it's going up 30 meters per second, right? Well, what does acceleration tell us? Acceleration is 9.8 meters per second squared, right? Let's just round that off. Let's just say it's approximately equal to 10 meters per second squared. What does meters per second squared mean? The acceleration tells us how much the velocity changes every second, right? So that means that the velocity changes by 10 meters per second every second, right? That's a more visual way of writing it. Meters per second squared, you're not really thinking about velocity changing, right? But if you think about it, it's the acceleration tells us that the velocity changes by 10 meters per second every second. And I'm rounding off from 9.8 to 10 so that I can do this in my head. Otherwise, I'd have to think too much. Okay, so we've got a question about the previous one. You always pick positive time. There's no, physically, time can't be negative, right? We pick positive time. Okay, so let's think about this. At t equals 0, the object leaves our hand, the ball leaves our hand at the top of the cliff, or wherever we are, right, at the top of the cliff, going up at 30 meters per second. Now, 1 second later, how fast is it going? If we had a strobe light going off and we were drawing a motion diagram, the ball would appear right there. So this is 1. It would be going 20 meters per second, right? Because acceleration of gravity is 10 meters per second. So it's gonna, because the ball is going up and gravity is pulling down, we get, the ball is slowing down, right? So now it's going 20 meters per second. And it's here, right? So this is at t equals 2 seconds. It's right there. The strobe light goes off. We see it right there. And how fast is it going now? 10 meters per second. You're catching on. And at t equals 3 seconds, what happens to that ball? It hits its highest point, right? And it momentarily comes to rest. So there it is right there. And v is equal to 0 at that instant. That's t is equal to 3 seconds. This is on the way up, right? Now on the way down, I can't, I'm going to end up drawing on top of myself here. So I'm just going to move the column over. We'll make another column for the way down. But really the ball goes up and it comes back down in the exact same line, right? So I'm going to redraw this. This is t equals 3. Start with that. V is 0. 1 second later, so we basically were letting go of something, right? 1 second later, what happens? If it's at the top, it's not moving. 1 second later, gravity's pulling on it. It's going to be going 10 meters per second in the downward direction. You following? And when the strobe light goes off at 4 seconds, where's that object going to be? It's going to be right here, right? One second later, at t equals 5 seconds, where's it going to be? It's going to be down here. And at t equals 6 seconds, it's going to be right back where it started, and it's going to be going 30 meters per second. Okay, so if our hand was still there, when we throw it up, it leaves our hand at 30 meters per second. 3 seconds later, it's at its highest point. It's momentarily comes to rest. Velocity is 0. Then it starts to come down. 3 seconds later, it's about to hit our hand, moving at the exact same speed it was going when it left our hand, 30 meters per second. And that's because we're ignoring air resistance. So if the acceleration is the same on the way up as it is on the way down, then it's going to be moving the same speed. It's going to take the same time to get up as it takes to come down, and it's going to be moving the same speed. If there's air resistance, of course, it's not going to be moving quite as fast when it gets to our hand, right? It loses a little bit of its energy to the air as it moves through the air. But in this case, with no air resistance, when it gets back to your hand, it's moving the same speed. So that whole first part of the problem, where it goes up, turns around, and comes back to your hand, didn't really matter. It ended up being the same problem. Those two problems ended up being exactly the same. Yeah, I guess I'm not writing velocity here. I'm writing here. I'll put, you want negative signs there? I was just doing the magnitude of the velocity, and I was using the direction of my arrow. Actually, I'm going to write it. I like the way I had it originally. The velocity is given by this whole thing, right? The arrow is pointing down. The magnitude of that arrow is 20 meters per second. Okay. The acceleration never changes. The acceleration is downward the whole time. The acceleration never changes. If you want to call down negative, it's negative the whole time. Okay. Good stuff. Let's do this problem. So I told you I was saving a special problem that would be pretty straightforward if we use our graphical approach, but would kind of be a nightmare to solve if we're using equations and things. And I'm not sure it's a nightmare to solve with equations, I'm not going to do it though. But I'll show you how you can solve this with our graphical approach. So we're given this problem. In a 100-meter race, accelerating uniformly, Laura takes 2 seconds, and Helen, what is that? Takes 3 seconds to attain their maximum speed. Then they each maintain that maximum speed for the rest of the race. They cross the finish line simultaneously, both setting a world record of 10.4 seconds. Find the acceleration of each sprinter, their maximum speeds, which sprinter is ahead at 6 seconds, and by how much, what's the maximum distance by which Helen is behind Laura, what time does that occur? Lots of questions here. I'm not going to answer all of them, but let's start working our way through this. Okay, so see if you can plot the velocity versus time graph for these two sprinters. Let's take a minute. I usually start with velocity versus time and see if that helps me. So I'll draw Laura in here. Let's see what color. I'll just use black. This is V.
So the first person, 2 seconds
to reach her maximum. What is it? And then they stay at their maximum speed for the rest of the race, ending there, right? So the second person takes 3 seconds to get to her maximum speed. I'll use red, I guess, so it's obvious. 3 seconds. And so this would be VH, right? Okay, this should be nice and continuous there, okay? Does that make sense? the one that takes longer to get to their maximum speed has to end up with the higher maximum speed in order to finish in the same amount of time. Are we all good with that? Hopefully we all had the same graph here now. Okay, so what do we know about these? We know that they both covered the same distance, right? It's a 100-meter race. So the area under these curves is the same. And we know what that is, right? 100 meters. So for Laura, we look at this, we have the area under the curve is 1/2 times 2 times their maximum speed plus the area of the rectangle next to it, which is 10.4 minus 2 times VL. And we know that has to equal 100 meters. And I get that the maximum speed for Laura, 10.6 meters per second. Okay. They both have different accelerations, right? One is quicker, but the quicker one doesn't hit as high a maximum speed as the one that accelerates a little slower. So they're quicker, they have a bigger acceleration, they get to their maximum speed sooner, but the maximum speed is not as high as the other person's. Okay, so now we could go through and solve for other things too. This is the only thing I've solved for right now, but why don't we could take a minute and solve for something else. You can see here that doing this graphically is pretty straightforward. I hope you realize this is one of those cases where the graphical approach is really nice. So whenever you have a race, somebody catching up to somebody else, or whatever is happening, in this case, they both started and ended at the same time, but one of them had a different acceleration. Oftentimes you'll see problems where one person has a head start, you know, one person, let's see if we had, so if you gave one person a 1 second head start, you'd have one person would be doing this. Let's say we wanted to know at what time. So here, let me write out more of the problem here. Give one person a 1 second head start. Both accelerate. This is another typical problem. Both accelerate with constant acceleration. At what time assuming the second person has a greater acceleration, of course. So there's our acceleration of person one. At some time, they are at the same place, but one of them started 1 second after. So they have to have a slope that looks like that. So this is person two. The acceleration of person two has to be greater than the acceleration of person one, right? So person one leaves the starting point. 1 second later, person two leaves. They both are accelerating uniformly. We want to know at what time does person two catch person one. So this is a tricky problem to do if you're going through equations. But if you know that, well, the areas have to be the same, right? The area of this triangle and the area of, what should I use? My highlighter. The area of this triangle both have to be the same. Then you could set those up, right? You know that 1/2 t times v max for person one has to equal 1/2 t minus 1 times v max for person two, and then we could plug in for the v maximum. We could solve for that using I think the accelerations were given. Okay, so these are a couple of examples where the graphical approach is really nice. Other than that, it's kind of, 6 of one, half dozen of the other. You usually end up using the graphical approach with the same equations in the end that you would get using the kinematics equations and making your table and getting the equations that way. But, do a few and see how you would solve them. Practice solving a couple each way and see what works best for you. Usually just, either approach is fine, but I just wanted to point out there are a couple of cases where we got these complicated problems with something passing something else that that the graphical approach is kind of nice. All right, so I'm going to shut off the recording here. I'll stick around for a few minutes if there are questions. Otherwise, feel free to join the office hour at 4 o'clock, and or I'll see you tomorrow.